We'll start in a couple of minutes at 9 o'clock. So we got the overhead working today. Was that kind of weird online yesterday?
Oh, no, we couldn't tell at all if
Yeah, it was, this was off kilter, so I had to sort of split the difference so the students that were in here could see what they were seeing online.
It worked perfectly fine yesterday, so.
Worked okay? All right, it's finally 9 o'clock. We'll be in section 8.2 again, area of a surface of revolution. So I added a few more textbook exercises. So just those 8. You can work on more if you like. So to summarize what we did yesterday, let y be a function f of x that is positive, and the derivative is continuous. Have you ever wondered why they mention that they want the derivative to be continuous? Well, that guarantees that we have a nice smooth function with no jagged corners anywhere. So we want smooth functions for our purposes. The surface area of the surface generated by rotating y equals f of x on the interval from a to b about the x-axis is this formula. It's the definite integral of 2 pi times f of x times the square root of 1 plus f prime of x squared from x equals a to x equals b. And then the Leibniz notation, if y equals f of x, instead of writing f of x, you can just put y. And instead of f prime of x squared, you can write dy dx squared. Okay, so let's do a couple of practice problems. Find the surface area from rotating y equals the square root of x for values of x from 1 to 2, and rotate it about the x-axis. Okay, so we just do the algebra and arithmetic. and the calculus. So think of y equals the square root of x if you want. Think of it as x to the 1/2. And so the derivative is 1 over 2 times x to the 1/2, or 1 over 2 times the square root of x. So we're going to need 1 plus the derivative squared inside the square root. So let's just find what 1 plus the derivative with respect to x squared is in our preliminary work. So we get 1 plus 1 over 4x. And oftentimes it's convenient to write expressions as a single expression instead of a sum or difference. So we have a common denominator of 4x, so we'll write this as 4x plus 1 over 4x. This is the expression that will go inside the square root. Okay, so the surface area that we get by rotating y equals the square root of x on the interval from 1 to 2 is the definite integral from 1 to 2 of 2 times pi times f of x, or y, but y is the square root of x, so 2 pi times the square root of x multiplied by the square root of 4x plus 1 over 4x dx. Okay, then we'll simplify the integrand. So you can probably tell right away what it's going to simplify to. But I'll put in a couple of steps. Let's write 2 pi times the square root of x. And I'll replace the square root of that rational expression with the square root of the numerator, 4x plus 1. And then the square root of 4x, the square root of 4 is 2, so I'm going to write it as 2 times the square root of x dx. And we get some cancellations. 2 divided by 2 is 1. The square root of x divided by the square root of x is 1. So I'll bring the constant pi out front. You don't have to, but... And then let's write down what's left. All that's left is the square root of 4x plus 1 dx. Okay, now what? You can think of the square root of 4x plus 1 as 4x plus 1 to the 1/2. If you want to, you don't have to go through the entire process, but if you use the substitution rule with u equals 4x plus 1, then du is 4 dx. And that means dx is du over 4. So we might as well do this. There might be some things about the substitution rule that not everyone is completely aware of. So let's go ahead and transform this. So I'm going to have, instead of the square root of 4x plus 1, the square root of u, I'll write it as u to the 1/2 for now, and replace dx with du over 4. And then what about the limits of this integration? What are the lower and upper limits after this transformation? Well, let's start with the lower limit. On the original one, when the integrand is expressed in terms of x, the lower limit is x equals 1. So after this substitution, this lower limit has to be a u value. So which u value is it? Yeah, we use this equation right here. Yeah, so up here, the lower limit is x equals 1. And this lower limit is u equals 4 times 1 plus 1, or 5. Right? Are we all in agreement? And the upper limit is u equals 4 times 2 plus 1, or 9. So in the next step, I'll do a couple of things. I'll divide pi by 4. In other words, move the constant 1/4 out and write it as pi over 4. And then an antiderivative of u to the 1/2 with respect to u is u to the 3/2 divided by 3/2. When you divide by 3/2, that's equivalent to multiplying by 2/3. So u to the 3/2, and then evaluated from 5 to 9. Okay, so our surface area, pi over 4 times 2 over 3 is pi over 6. And then replace u with 9, we get 9 to the 3/2. And then minus 5 to the 3/2. So this is an okay answer if you want to leave it in that form. You could write it 9 to the 3/2. So that's just 27, right? The square root of 9 is 3, and 3 to the 3rd is 27. And then minus 5 to the 3/2, that is 5 times the square root of 5. Okay, so that's the surface area in square units, whatever the units happen to be in. Okay, let's do another one that's pretty straightforward also. Find the surface area by rotating y equals x to the 3rd for values of x from 1 to 4 about the x-axis. Okay, so we want to find the derivative of y with respect to x. This is just 3x to the 2nd. And we want to know what 1 plus that derivative squared is. So we get 1 plus 9x to the 4th. And this is the expression that goes inside the square root. So we can write down the surface area is the definite integral. The lower limit is x equals 1. The upper limit is 4. And then 2 times pi times y, but y is x to the 3rd. And then multiplied by the square root of 1 plus 9x to the 4th dx. Okay, this one also works out pretty nicely. Inside the square root, 1 plus 9x to the 4th. So if we use the substitution rule, we can assign u to be 1 plus 9x to the 4th. And so du, what's du? Yeah, Yeah, 36x to the third, and then don't forget the dx. So in our integral, we see the x to the third dx, and we just need to account for 36. So if we divide both sides of this by 36, du divided by 36 is x to the third dx. So we can make those substitutions. And we'll have to find the limits of integration. We'll do that in a minute. But since I'm replacing x to the third dx with du over 36, I'll go ahead and put the 1 over 36 out front for now. And then on the inside, 2 pi. And we have the square root of u, but I'll write it as u to the 1/2 again. And then du. So I think everything is accounted for. We just have to find the limits of integration again. So in the original integral, the lower limit is x equals 1. So for the transformed integral, the lower limit is u equals 1 plus 9 times 1 to the 4th, or 10. Is that what you get? And the upper limit, when x is 4, u is equal to 1 plus 9 times 4 to the 4th. So let's see, 4 to the 4th is the same as 2 to the 8th, which is 256, right? And then 9 times 256. Well, gee. So that's 2560 minus 256. So 2304, and then plus 1. I get 23 over 2,305. Is that what you get for the upper limit? So what did we get ourselves into? Okay, so let's go ahead and evaluate the integral. So I'm going to write 2 pi over 36, but write it as pi over 18. And then an antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2, or 2/3 times u to the 3/2, evaluated from u equals 10 to 2,305. So this is going to be pi over 27 when we simplify pi over 18 times 2/3. And then I'm just going to be satisfied with replacing u with 2305, raising it to the 3/2 power, and then minus 10 to the 3/2. So okay, let's move on to the next page. Okay, some of what follows might seem weird, but we can make sense out of it if it is sort of counterintuitive. So we're going to assume that the functions are positive with continuous first derivatives. Smooth functions. The surface area generated by rotating y equals f of x for values of x from a to b about the y-axis, not the x-axis. We're rotating about the y-axis. And that is the definite integral from a to b of 2 pi x times the square root of 1 plus f prime of x squared dx. So I'll just highlight that this is rotating about the y-axis, or rotate f of x about or around the y-axis. Let's just write down the formula if we rotate f of x about the x-axis and just look at the comparisons. Rotate f of x about the x-axis. Our formula for that surface area is S equals the definite integral from a to b of 2 pi f of x times the square root of 1 plus f prime of x squared dx. Okay, so maybe it makes sense to you. The first time I saw it, I thought, well, this is kind of weird, but it makes sense. So what's going on here anyway? I can attempt to explain it graphically. So suppose we have some nice smooth function y equals f of x. And then on the interval from a to b, if I rotate about the x-axis, so we sort of talked about what that looks like yesterday, rotate that about the x-axis, then the radiuses of if you rotate that and take a cross-section, the radiuses are f of x values, right? The distance from the x-axis to this point on the curve, we could describe that as the radius of a cross-section of the revolution. So f of x is the radius in this case. So if we're rotating about the x-axis, that's what we want this to represent. In our construction of this yesterday, this f of x is the radius of the cross-section. Okay, but if we rotate this about the y-axis, well, remember what this expression represents, the square root of 1 plus f prime of x squared dx. It represents the length of the curve, or the arc length. So the arc length is the same whether you rotate it about the x-axis or the y-axis. So this part isn't a problem. But if we rotate about the x-axis, or a radius of a cross-section of that rotation is a what? It's an x value, right? Because we're rotating this curve starting at x equals a and ending at x equals b. And so a radius of a cross-section of that revolution are x values between a and b. See what I mean? So that's where this x comes from. This x represents a radius, just like f of x does when we rotate f of x about the x-axis. Okay, so it does make sense. There is an alternative which we will look at here in a second. The alternative could be a lot more work, though. So on this graph of this y equals f of x, let's suppose the y-coordinate of this point is c, and the y-coordinate of that point is d. So what we could do is we could, if it's a one-to-one function, we could easily define x as a function of y, which would give us the same curve as y equals f of x, only on the interval for y values from c to d. See what I mean? So this is the alternative. We could find x equals g of x for x equals g of y for values of y between c and d that is equivalent or the same curve as y equals f of x on the interval from a to b. Okay, so that gives the same curve. As y equals f of x for values of x between a and b. Okay, then if we succeed in doing that, I'll just show you this formula, which is what we would do if we didn't have to make that transformation. So this says, and this corresponds exactly to the original situation. If the curve x equals g of y for values of y between c and d is rotated about the y-axis, then the surface area generated is this definite integral in terms of y. So the definite integral from y equals c to y equals d of 2 pi times g of y times the square root of 1 plus dx dy squared dy. Okay, so this amounts to the alternative if you want to go to all that work, but the easier thing to do would just be to use this formula if you're rotating y equals f of x about the y-axis. Okay, but along the same lines, if we have the curve x equals g of y for values of y from c to d, and if we rotate this about the x-axis instead, then the surface area generated is the definite integral from y equals c to d of 2 pi y times the square root of 1 plus dx dy squared dy. So we're not using g of y this time, we're using y. Well, how would you explain that? I know I'm being repetitive, but
That seems to be the same thing that we did with the other way around, just rather than the explanation you used before where you were just changing the radius of the cross section from one to the other because you're switching the axes while using the same equations, the same integral.
yes.
I don't know if the way I explained that makes any sense, but it's essentially the same transformation when we took y equals f of x and switched it to be rotated around the y-axis with the other equations and stuff. Right?
Yeah, I think you have it. So this time we have function x equals g of y. So I was sort of careless in my sketch, but if we're going to rotate this about the x-axis, then a radius is a y value between C and D. The radius of a cross-section of the revolution is a y value. So that's why this y is there if we're going to rotate it about the x-axis. So that's the radius of a cross-section of the revolution. Okay, so that's the idea. You'll see some of those in the exercises, a couple of the exercises that I assigned for practice. Okay, let's try this one. Find the surface area by rotating y equals 1/3 times x squared plus 2 to the 3/2 for values of x between 1 and 2 about the y-axis. Since we're rotating about the y-axis and we're given y as a function of x, then what formula do we use? Let's just sketch or write down the formula for the surface area in this case. So it's going to be the definite integral from a to b, where a and b are the x values on the endpoints of the x interval. And then 2 pi, then what? So we're rotating a function of x about the y-axis. So it's going to be x. 2 pi x, not f of x. I'm not calling that f of x, but this is what f of x is. And we're going to put x there instead, and then the square root of 1 plus, I can use the Leibniz notation for the derivative of y with respect to x. Okay, so we have to find the derivative of this function y, then square it, add 1 to it, and put it inside the square root, and then go from there. So we'll do that preliminary work. The derivative of 1/3 times the quantity x squared plus 2 to the 3/2 with respect to x. So we have 1/3 times 3/2, which simplifies to 1/2, and then times x squared plus 2. 3/2 minus 1 is to the 1/2. And then the derivative of the inside function is 2x. We're just applying the chain rule. And 1/2 times 2x is just x. So let's write it as x times x squared plus 2 to the 1/2. And then we're going to square this derivative, add 1 to it, and put it inside the square root. So let's just write the 1 plus the square of the derivative. Hey, when we square the derivative, we're going to get x squared times the quantity x squared plus 2. And since what we're looking at is pretty nice. It's going to work out pretty nice. Let's go ahead and simplify this by multiplying. So we get x to the fourth plus 2x to the second plus 1. This is what's going to go inside the square root in the surface area formula. But do you recognize x to the fourth plus 2x squared plus 1 is sort of a, yeah, it's a perfect square. So we can think of x to the fourth plus 2x squared plus 1 as x, the quantity x squared plus 1 squared. So this is going to work out pretty nicely since we're going to, in a minute, we're going to be taking the square root of the quantity x squared plus 1 squared. Okay, but let's go ahead and write the surface area formula, or apply the surface area formula. The interval of integration is from 1 to 2. 2 pi x, because we're rotating about the y-axis, and then times the square root of the quantity x squared plus 1 squared dx. So this is going to turn out to be pretty easy. The square root of x squared plus 1 squared is x squared plus 1. So we get, well, let's see, 2 pi and then x to the third plus x in parentheses dx. So now we can find the antiderivative, 2 pi and then x to the fourth over 4 plus x to the second over 2 from 1 to 2. Okay, 2 to the fourth is 16. 16 divided by 4 is 4. Plus 2 to the second divided by 2 is plus 2. And then minus 1/4 minus 1/2. So just a little bit more work here. So 6 minus 1/4 minus 1/2 is 6 minus 3/4, which is 5 1/4. 5 1/4, so that's 21/4. And then 2 pi times 21/4 is 21 pi over 2. Are we all in agreement? Okay, the next problem. In this one, we'll get to review some other material that will be on test 2. Test 2 is 2 weeks from this Friday. Well, not only the surface area part, but something else that from chapter 7. Let's set up the integral for finding the surface area generated by rotating y equals 1 over x for values of x greater than or equal to 1 about the x-axis. Okay, so just observe what's implied by x values greater than or equal to 1. In other words, what's the interval of integration going to be? 1 to infinity, yeah. So this is going to involve an improper integral. The limits will be from 1 to infinity when we set up the integral for surface area. Okay, but we go about finding the integrand the same way that we've been doing. So you can think of 1 over x as x to the negative 1. And so dy dx is negative 1 over x squared. And inside the square root of the surface area formula, we want 1 plus the square of the derivative. So 1 plus, and then when we square negative 1 over x to the second, we get 1 over x to the fourth. And let's write it as a single rational expression with a denominator of x to the fourth. So 1 plus 1 over x to the fourth becomes x to the fourth plus 1 over x to the fourth. Okay, this is what goes inside the square root. So we can write the surface area. This is going to be an improper integral. The lower limit of integration is 1, and the upper one is positive infinity. And then 2 pi. So what comes next? We're rotating a function of x about the x-axis.
F of x, so 1 over x, right?
Yeah, it's what f of x is, but even though we're not using f of x, it's just 1 over x. So 2 pi times f of x times the square root of 1 plus f prime of x squared. And that 1 plus f prime of x squared turns out to be x to the fourth plus 1 over x to the fourth. That's all inside the square root. Okay, so a little bit more work here. Well, we can do a couple of things at once. The square root of x to the fourth plus 1 over x to the fourth. I'll put the square root of x to the fourth plus 1 in the numerator. And we know that the square root of x to the fourth is just x to the second. Okay, then let's write this as 2 pi times the improper integral from 1 to infinity of the square root of x to the fourth plus 1 over x to the third dx. Okay. So now we have an improper integral. What do you remember about evaluating improper integrals as far as the answer? Yeah, one of two things will occur. Either the improper integral converges to a finite number, or it diverges to one or the other of the infinities. So what do you think about this one? Do you think this one converges? Okay, this is perhaps a good opportunity to review the, what do they call it? The comparison rule from chapter 7, or the comparison test, I mean. So I'll just jot down if 0 is less than or equal to g of x, which is less than or equal to f of x, for values of x greater than or equal to a. So in other words, the x values go from a to infinity. Okay, then if the improper integral from a to infinity of f of x dx, if this is convergent, then that means the improper integral involving g of x is also convergent, because g of x is smaller than f of x. This is also convergent. And then what's the other half of the comparison test?
If g of x or that integral is divergent, then so will f of x over that integral.
Yeah. If the improper integral of g of x from a to infinity is divergent, then so is the improper integral from a to infinity of f of x. That is also divergent, right? Okay, so I'll have to use some scratch paper. We're just trying to find if that improper integral converges or diverges. If it converges, then maybe we can find what it converges to. So I saw one vote for convergent. Any votes for divergent? Okay, let's try this. So if you compare, this is for x values greater than or equal to 1. If you compare x to the fourth, the square root of x to the fourth plus 1 with the square root of x to the fourth, which one is bigger and which one is smaller? Not a trick question, but
X to the 4 plus 1 is 1.
yeah, the expression on the left is greater than the expression on the right. And the square root of x to the fourth is just x to the second. So we can say that this, the square root of x to the fourth plus 1 divided by x to the third, that's greater than x to the second divided by x to the third. But x to the second divided by x to the third is 1 over x. And what do we know about the improper integral of 1 over x dx from 1 to infinity? So a few days ago, more like weeks, we found that this is divergent. And it's not too hard to prove, because an antiderivative of 1 over x is the natural log of x from 1 to infinity, or the limit as b goes to infinity of the natural log of x from 1 to b. So the limit as b approaches infinity of the natural log of b minus the natural log of 1. The natural log of 1 is 0. So we get the limit as b approaches infinity of the natural log of b. The natural log of b goes to infinity as b goes to infinity. So this goes to infinity. So this is divergent, but since the other function is greater than 1 over x for values of x greater than or equal to 1, this is also divergent by the comparison test? Isn't that right? 1 over x is smaller than the square root of x to the 4th plus 1 over x to the 3rd for x greater than or equal to 1. And since the improper integral of 1 over x from 1 to infinity diverges, then any function that's greater than that one on the same interval will also diverge. So the answer is divergent. So are we all in agreement about that? Okay. Well, there's a little over a minute left. This is the same function y equals 1 over x, but this time the interval is of finite length. So we already did the work on this one. The surface area that we get by rotating y equals 1 over x about the x-axis on the interval from 1 to 2 is the definite integral from 1 to 2, and then 2 pi, let's see, I got rid of the 2 pi. Yes, so we're okay. So this was 1 over x times the square root of x to the 4th plus 1 over x to the 4th dx. But this simplified to 2 pi, the limits are from 1 to 2, and then the integrand is x to the 4th plus 1 over x to the 3rd dx. So see if you can find an antiderivative for the square root of x to the 4th plus 1 over x to the 3rd. I'll give you a hint. If you assign x squared to be tangent of u, and then just use that trig substitution, you should be able to eventually find the value of that integral. Okay, we're out of time for today. On Friday, we'll start section 8.3.